Since we've talked about how velocities added together when going from one reference frame to another can't be done in the simple case of just addition, it's also a good idea to see what happens to momentum in this sort of scenario. So if we are imagining there was some sort of ball and it were moving away from us at 99% the speed of light, and in that ball's moving frame there is some other object coming at it at 0.2 times the speed of light. So in that case, it's measuring mu prime, that's the velocity it measures the ball coming at, and it collides, according to it, at 0.2 times the speed of light. Well, if you're this outside observer, here, say, on the Earth, being nice and stationary, well, you would expect then that this thing would get an extra boost in its speed. But if you just did straight up normal momentum conservation, what would happen? Well, you would actually end up expecting this thing to start going then faster than the speed of light. We saw before that that's not going to happen. We need to actually now change our definition of momentum to be consistent with our Lorentz transformations. So, the classical definition has to go out. Fortunately, though, the new version is rather simple looking. Momentum in the relativistic system is simply the same as our original form, but with a multiplicative factor of gamma. And remembering that gamma is defined as 1 over the square root of 1 minus v squared over c squared. So this basically means that while, of course, any object will have some sort of maximum speed ultimately, we saw before there's no way we're going to be getting collisions and then have something go at or greater than the speed of light, this factor can get much, much larger. It can go anywhere from 1 to up to infinity. So there's no limit on momentum, and with this new definition, when we go from one reference frame to another, we can still have momentum be conserved with collisions. If we change the definition of momentum, though, we've changed something else. One of our fundamental laws is that there's a relationship between force and momentum. Namely, force is the time derivative of momentum. So if we have changed our definition of momentum in this case, that means we've also adjusted how we are going to be applying force. Now, in particular, this is going to have another interesting result, because remember, there's also a relationship between applied force and work. So, for example, work is change in kinetic energy. So let's take the case where we have some object initially at rest and we do some sort of force to it. So it starts with 0 kinetic energy and then it comes to some new final kinetic energy. And just for simplicity, we'll just say Ke without the subscript. So this is the amount of work done going from rest to some new amount. And from our relationship of what is the work energy theorem, the amount of work done is then what force is applied and over what distance. So from some initial to some final position. And we can substitute in, of course, our definition of force here, relating it to momentum, plugging that in here. Let's give ourselves a little bit of space to work this out. So we're going to find then that we can plug in a few things, and so we're going to be taking an integral of dp dt times dx. And now we have, of course, some fun stuff going on with that integral. So let's take a look underneath there. So we're taking a time derivative of our new momentum definition. Take that part out, and we're now looking at mu m times the speed we're going divided by 1 minus u squared over c squared. So this is a fun bit of derivation-y stuff, but it can be shown to work out as mass times the change in speed as a function of time divided by 1 minus our velocity squared over c squared to the 3/2 power. All right, not too bad. So that means now we need to plug this into our force equation. So we'll set that off to the side here. And we now find that our kinetic energy is going to be the integral, and now with respect to time instead, we can plug that in for. We can do that since we can use the definition that an infinitesimal amount of distance traveled, a little dx, is the same as velocity times the amount of time gone by. And we're doing this ultimately since it actually is going to make our equation solving a little bit easier. So we're going from some time 0 to whatever our new time is. So we're going to have mass times du dt. Dx is now u times time, all divided by our rather funky denominator to the 3/2 power. This looks like a nasty integral, but notice now that actually we have a dt times dt. We actually having these two cancel out. And so we can also move the mass term out of our integral. Do that, so we're going to have mass times integral, and now we're doing this with respect to du. So we're going from no velocity to whatever our new velocity is. We can substitute in that way. So we're going to basically have u du divided by 1 minus u squared over c squared to the 3/2 power. This is a fun little integral, but it works out such that when we also then plug in our integral limits of 0 and u, we're going to get mc squared divided by square root 1 minus u squared over c squared minus mc squared. I imagine one of those terms looks a little bit familiar, doesn't it? Well, here's the interesting thing. The 0 case, that was supposed to be when there was no velocity, when the thing was just at rest. So if we had only a tiny change in velocity, well, of course, this term will be will be some amount greater than just mc squared, but even at rest, there's still this little amount we're supposed to be subtracting off, as if at rest there is some amount of energy. So we're going to call this the rest energy. So our equation has this form. We can simplify this because we realize, oh, this is 1 over gamma here. If we take 1 divided by this is just gamma. So we'll simplify this, and this is now just gamma minus 1 mc squared. And we can, like I say, refer to this part of our expression as the rest energy is equal to mc squared. Well, you've definitely seen this equation before. We have just proved that a mass just sitting there has some amount of energy related to how much mass there is and the speed of light squared. So in this case, we may not want to just refer simply to the kinetic energy of a body, but its entire energy. And so if we wanted to do that, we would say that the energy total is just going to be gamma mc squared. It's just simply the addition of the kinetic energy and the rest energy. And so that's the total energy in any given body. Now, since usually we can't, just have the rest energy popping out, we would just, consider one aspect of this term here for the amount of energy in some body. But if we, of course, get into some of that nuclear physics stuff, we talk about atomic fission and fusion, we can talk about actually how mass converts to energy, and then it gives it an extra kick of kinetic energy. And that's pretty much the basis of all atomic power and atomic weapons. The fact that we can somehow, sometimes extract this rest energy and turn it into kinetic energy and really give things a punch. To even more fully express what might be going on, we can do a final expression if we were to say square both sides of this equation here for the total energy in a body. So we'd have energy squared equals gamma squared, mass squared, speed of light squared. May not look too pretty, but we also know that how the momentum, at least the magnitude of the momentum, is just gamma mass times velocity. And of course, we can also talk about the rest energy as mc squared. We can actually, with some careful algebra, show that this energy term squared is going to equal momentum squared times the speed of light squared plus the rest energy squared. This, of course, has an interesting thing that will pop out of that, is if we were to plug in, say, what's supposed to be the mass of light, which is supposed to be 0, then we find out that, oh, the photon, light, well, it still has to have some energy. We know that light has energy. But even if it's massless, it can still have momentum. Interesting thing. And also it means that we could then talk about how rest energy could then become the momentum in some body after either a collision or some sort of atomic reaction. So we can have this complete totalizing energy conservation principle even with all of the effects of relativity.